I've recently been doing a series of video documentaries on various older types of multimeters and voltmeters and so on, and I still have more to do, but today I'm going to focus on quite an old AC/DC voltmeter produced by the Weston Electrical Instrument Company of Newark, New Jersey. This is their model 341 voltmeter, and it dates from 1936, maybe a bit older than that. This is a high precision voltmeter, as it says on the meter face, alternating and direct current from DC up to 25 to 1,000 cycles. That should be cycles per second, I believe, so hertz. And there's the name badge, the model 341, and a serial number, Weston Electrical Instrument Corporation. And there's the zero adjust stuck right in the middle of the label. That's the zero adjust for the meter movement. This meter has terminals for 600 volts, for 300 volts, for 150 volts, all full scale. And this thing, which is a little hard to figure out what it's actually trying to show, but what that's supposed to be is a plus minus symbol. It's just that the bottom part of the plus is kind of gone or faded out, so it just looks like a weird shape, but it's supposed to be a plus over a minus. This is the common terminal here. You might call it the negative terminal of a normal meter or voltmeter or multimeter. And this other thing which looks like a terminal is actually a button, a momentary push button. It's a big, heavy, I don't know what metal it is, it's very heavy. I can barely pick this up with one hand, actually. There's a grounding strap. I think the front of this is Bakelite. And that grounding strap goes to a screw, which I think is one of the screws that holds the meter, the front of the meter movement into the case. There's a corresponding screw there, for example. And there are the two terminals of the meter, the electrical terminals, that is. And just some very simple wiring. One of them going around and up this way, the other one going down and around and up that way to this set of contacts. I'll make sure I don't drop this and break it. It's just a very simple leaf switch, which is operated by that, see if I can do this. You can see the contacts closing there when I push the button. So the push button is in series with the meter movement. And then you've got the wiring from the 600 volt terminal disappearing back there, and the 300 volt terminal coming around this way, the 150 volt terminal coming up here, and the common terminal there. That's the one that goes back around directly to the meter movement. So what are these things up at the top? Well, these are all wire wound resistors on insulating cards. There's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of these cards with wires wound around them. Different gauge wires, although most of them are the same. In other words, the cards are identical for the most part. I think there's a couple of them that are different, but like this one seems to have the windings more widely spaced, but in general they're the same value, I believe. Then there's also this insulating card up here, which is just home to a pair of capacitors, which are wired in parallel. And those come down to that side of the parallel capacitor, and also through that wire up around here. So what makes this meter special or noteworthy? Well, the first clue is that it works on AC and DC, but there are no selector switches to select between them. There's no rectifier at all, and there are no separate terminals for AC and DC, which you might expect if there's no AC-DC switch. So what gives? Well, this is what's generally known as a transfer type instrument. And all that means is that it's one that may be calibrated, for example, using a DC source, and then used without modification to measure AC sources. So you could calibrate it with one type and then use it without further calibration or adjustment to measure the other type of signal. Another clue is that there's only one scale, really. I mean, there's ones that end with the different voltages. So you've got one that ends with 150, one that ends with 300, one that ends with 600. Just depending on which set of terminals you use for that. But there's no separate scale for AC and DC, which you would normally expect on any kind of a multimeter that can measure both. And that's just because the rectifier that you normally find in such equipment would have an effect on where the pointer goes for each voltage. So that's another clue. Instruments like this are also known as electrodynamic instruments, or sometimes called dynamometer types, or my favorite, the electrodynamometer type of meters. I love saying that, electrodynamometer. So what does that mean? So here's a really poorly drawn and simplistic version of a typical moving coil meter mechanism or movement. You've got a couple of permanent magnets, north and south, for example, and then you've got the pointer, and it's on a pivot, and then you've got this armature here, and there's going to be a coil wound around it, which makes its way off through some very flexible wires that should not affect the movement, don't add any appreciable drag, and then you apply current to go through that and out. And that sets up a magnetic field on the armature, which reacts against the permanent magnet, and that causes the needle to deflect. And then there's typically a coil spring which tries to bring the meter back to here, and then the magnetic field set up by the current going through the armature coil is what works against the magnet to move the pointer over, typically to the right. Now if we make the permanent magnets into an electromagnet with, a pair of coils, essentially setting up a north or a south or what have you, and you keep the moving coil the same, now you can get some interesting interreactions. If you just apply a static current through the field coils, then they'll react, or they'll act just like the permanent magnet did, and when you apply a current through the moving coil, the coil on the armature, then you'll get the same exact thing as the normal movement. But what if you, for example, applied a voltage across the field coil and passed a current through this one, and maybe those are both from the same thing. Maybe you're trying to measure current against voltage, this thing could become a wattmeter. Or if you hook it up in another way, it could be an ammeter. Depending how you connect the moving coil winding and the field coil windings, this could be a voltmeter, it could be an ammeter, it could be a wattmeter. And this is the essence of a dynamometer or electrodynamometer type of movement. Now, you've got these two fixed coils and they're symmetrically situated. And if you provide a fixed or static current or voltage on these, so it sets up a static magnetic field, and you apply a voltage across this or put a current through it, either way you're still getting a current through it, it's going to, like I said before, act just like a normal two-terminal meter movement. If you're using it on DC, it'll do exactly that. But what if you applied AC to this and you still have the static DC voltage or current on the field? Now the pointer will try to swing one way when the AC is at one polarity, and when the AC alternates and flips the other polarity, it's going to try to do that. So the meter is going to try to whip back and forth when you've got AC on this coil. Although if it's a lower frequency like power line frequencies, just the natural damping of the mechanism would probably result in the meter just sort of sitting in the middle and quivering a little bit, if it even does that visibly. On the other hand, what if, for example, you did this? You connect one end of the field coil to one end of the moving coil, and then bring your signal under question to these two terminals, one the opposite end of the field coil and the opposite end of the moving coil. So their polarity always remains consistent between the two of them. When you're measuring DC, you're going to get a static field here and a static field here, and based on the strength of the field, you're going to get a meter movement. But if you put AC on it, the magnetic polarity of both will constantly reverse with the alternating current, but they're still in the same relationship to each other they would have with DC. Therefore, it makes no difference whether you put AC or DC on this. The meter still deflects upscale for more voltage, and that's why these electrodynamometer type meters can measure AC and DC without anything else being different. You just apply the different signals and the meter has no difference in its wiring or its components or its scales or anything. So looking at the back side here again, you may wonder, why is there this big metal can surrounding the meter movement? And that's for a good reason. The field, or the magnetic field produced by the fixed coils, or the field coils, is weaker than you would typically get from permanent magnets in other types of meter movements. And especially when you're measuring DC, so you don't have that reversing polarity of the AC signal. So you're measuring DC, the field coil's already setting up a pretty weak magnetic field, and the Earth's magnetic field can interfere with it. It can have a significant impact on the readings. It can skew it and cause bad accuracy or just weird readings. So electrodynamometer type instruments need to be shielded from stray magnetic fields, whether from nearby equipment or just from the Earth's magnetic field. So you almost always see these enclosed in a casing which is made out of a high permeability alloy. Now a bit more about this. All these resistors, wire wound resistors here, Another characteristic of this type of meter is that they tend to be pretty low impedance, and as a result, you know, the amount of current that goes through them is higher than you'd normally see with other moving coil meters, and therefore they can have an effect on circuits they're connected to, more so than you would normally see from, say, a typical multimeter being used as a voltmeter or whatever. So let's say that these, just for the sake of discussion, that this amounts to 11 resistors, and each one has a terminal on the left, and then you have the winding or the wound resistance wire going around the card many times, and it ends up on the card on the opposite side. And by jumpering the tabs on two adjacent cards, like you see right there in the middle of the screen, that's coming from the card above and going to the card below, and you can see additional jumpers on every pair of cards, and then going around the other side you have the same thing but on different pairs. So this one here, you have a wire coming in to the top card, but it is not jumpered to the next card. On the opposite end of that card, you have a jumper going to the second card down, which in turn jumpers to the third card down, and so and so and so, and finally you come out on the bottom one with a wire that goes down to the meter movement. But there's also a wire coming up to here, so what is that like really? So here's a little sketch I made. The resistors essentially become a big voltage divider, just like you'd see on any other voltmeter. More resistance is used for higher voltage ranges, so if you're using the 600 volt terminal, you have to go through all the resistors before you get to the meter movement. 300 volt terminal, you have less resistance. 150 volt terminal, you have the least resistance. Let's just say that we're just using the 150 volt terminal. Oh, I should go back and say this top resistor is made out of 5 of those resistor cards in series. So 5 of them are used to make up just this one resistor. And it's somewhere in the area of 7644 ohms. The next one has 3 resistor cards in series, coming to something like 3822 ohms. And then the remaining 3 are also connected 3822 ohms approximately. So you can see that with 150 volts you're going through a 3822 ohm resistor and then down to the meter movement. If you're going through the 300 volt terminal, you're ending up with double that, 3822, right? That ends up being 7644 ohms. And then if you go to the 600 volt terminal, which is twice 300, you add another 7644 ohms. So each time we're doubling the resistance in a geometric progression. The bottommost resistor here has the 2 capacitors wired across it. And here's that momentary leaf switch, the push button operated leaf switch, then the meter movement, and then the plus and minus common terminal. So since all moving coil meters are essentially ammeters, and it's just how you hook them up externally that makes them measure voltage or wattage, for example, instead of just purely current, when you connect an external voltage through a series resistance and then through the meter movement, it turns that into a voltmeter. And it couldn't be any simpler than that. This pair of capacitors here, I think they're just there for best performance when you're measuring AC. They may actually not be smoothing, because I would assume if they were smoothing they'd be right across the meter movement instead of across the series resistor. So what is that actually doing? Well, as you apply higher frequency AC to this, these capacitors are going to start looking less like an infinite resistance and more like a lower value resistance. So they're going to kind of snub the lowest resistance that everything goes through, no matter which range we're in, and lowers its resistance ever so slightly. So this may in fact be a very tiny compensation for when you're measuring higher frequency AC. Otherwise, I don't see where these would come into play at all. I think it's just a compensation for the higher frequency range, which, as I already mentioned, can go up to around 1 kilohertz on this. And finally, why is there that push button? Well, I think it's because this meter presents a substantial load to the circuit under test, and you might want to connect up test leads to something that you're testing, but not always have the meter in the circuit. Only have it in when you want to take a reading and then remove it. The other thought I have on this is that because a fair amount of current goes through this, if you kept measuring for a long period of time, those resistors probably start getting pretty warm. And having a momentary push button here is probably a device to minimize the dissipation that you're going to have in these resistors, and maybe even in the meter movement itself. So in other words, you can leave the test leads connected up to the circuit or whatever you're measuring, and only push the button when you actually want to take a reading. Alright, let's try a little demonstration of this on DC. I don't have any handy higher voltage DC sources, and without rigging something up, I'm just going to use my normal bench supply. I've got 2 channels tied in series, so I should be able to get up over 60 volts. And on the 150 volt scale, that'll at least get me, you know, a third of the way or so up. Although I should note that this scale is not linear, and that's probably a characteristic of this type of meter. You know, things are kind of bunched together at the left end and then they spread out as you go up. So I might only be able to get up around 60 here on the 150 volt scale. I'm going to start with both supplies turned all the way down, and I'm going to go up to 10 volts. Let's see here. To 10 volts there, and I'm going to push the button. Well, I have to turn the supplies on first. That always helps. I'm going to push the button, and I get a very small meter movement. 10 volts is way down here at the bottom of the scale. So I really need to get about 40 volts here and if I'm going to see much of anything. So I'm going to crank this guy up to about 20, change over to this guy, and go up to about 20 volts on that one too. Push the button, and sure enough it's sitting right about on 40 volts when I push the button. Now I'll take this guy up to 30 volts and set my other one to 30 volts while I'm at it. So now I should get 60 volts when I engage this thing. Right on the money, 60 volts. Okay, now I've got some test leads hooked up once again to the common and the 150 volt terminal, and they're hastily rigged up to a pair of banana test leads which go into my AC access panel, which is soon to be plugged in to my Variac. I'm on the 140 volt range. That's the most I can get out of that. I'll turn this guy on, and once again I'm not going to get a reading until I push the button down here, but I'm going to crank this guy up to about 60 volts, as near as I can tell on the meter there. And then if I push the button here, you know, just a little bit shy of 60. The Variac meter tends to read a bit high, so I think this is more accurate than the Variac. It's reading just ever so slightly high, and my fluke says that it's about 61 volts, so that's pretty darn good, especially considering the age of this guy. Let's go up to about 100, and I'll check it real fast while I'm talking here with the fluke. Yeah, it's really close to 100, so let me push the button here. It's reading a little high, and I think the fluke said, I'll double check it now, I would say this is reading about 102 volts. And the fluke says 103.5. And I'll go up to the maximum this guy can do, which is going to be a bit shy of 150. And it is just a little shy of 150. So that's about right, actually. So you can see it's working with both AC and DC. Now what if I go to the higher voltage range? I'm going to move this test lead here over to this guy, the 300 volt range, and push the button. So 150 is that mark between 140 and 160, and so the 100, it's like 100 reading 140, 142 on here. It's going to be increasingly inaccurate as I go up in ranges. Now if I go to the 600 volt range, I still get a reading, but it's really low. Let's see. It's interesting that the scale doesn't even start until 160 on the 600 volt scale. So you're down here in the nether regions where you can't really tell what it is. But we are getting a reading, and that's just proof that all of those series resistor cards are intact. None of them are opened. So, is there more to this beauty than just what I've shown? And there is. It comes in a beautiful wooden case, which I had to do some restoration work on. First off, it has the meter front panel mounts with 4 screws on the corners, and those go into these sliding threaded metal collars here, and those, you know, allow some slop, so in case things aren't completely lined up they can still align a little bit with the screws. That's kind of a nice feature. When I got this, one of these was totally broken out. I'm trying to remember which one it was now. I can't even tell. I think it was probably this one, that the screws had fallen out. They were rattling around loose in here, and this whole bracket was just attached by its screw to the back of the front panel. And so I did some remedial work with epoxy and so on, and filled the holes and then re-drilled them, remounted the bracket, did some other minor repairs. The handle that was on here, this beautiful leather handle, this is not the original. The original one looked just like that, except that it was, the leather was just cracking and turning to dust. And it's a nice contoured handle too. It's not just flat leather. It has a somewhat rounded shape to it, makes it more comfortable. and it can kind of push down flat or flat-ish like that, and then when you need it, pulls it up against these metal brackets. Makes a nice comfortable carrying handle. Anyway, I took the original handle into the local shoesmith, who also repairs a lot of saddles and does other kinds of leather work. He's made seats for my high wheel bicycles for a long time. He's an old school, is artisan the right word? From Russia, and he does really nice leather work, I think, and I showed him the old one, and he made this nice one for me. I still need to do a little bit of cleanup in here just because there's a little dust, but some of that's probably quite old and is kind of stuck to the lacquer. Anyway, you can see from the air vents that they were expecting that top part of the meter guts to get warm, so there's a place for air to flow in and warm air to flow out. So there's very good passive cooling of the resistors in there. So obviously they're intended, well, if not intended, they're expected that they're going to get pretty warm. And then there's a couple of cutouts on the back of the case, no doubt to clear some taller things on the guts. Alright, there's the way it fits into its case. And there's more. There's this equally attractive cover for the case. Which goes on with hook type latches, or rather latches that work like this. Isn't that a beauty? Here's what's inside the cover. It's sort of a certificate that's held in by brackets at the corners. There's also a government tag exempt. Government tag exempt? I don't know what that means. Thought it said tax exempt at first. So a Weston AC DC voltmeter model 341. Serial number is written on there. This instrument is an electrodynamometer voltmeter. It indicates absolute volts, and if properly used, its indications may be relied upon to within 0.25% of full-scale value on direct current or alternating current of any frequency from 25 to 1,000 cycles per second, or 25 to 1,000 hertz. It is shielded from the effect of external magnetic fields. To obtain the greatest accuracy when used on direct current, the mean of reversed readings should be taken to eliminate the effect of any slight residual magnetism in the shield. For ordinary measurements, no corrections are necessary for temperature or frequency. When great accuracy is desired, correct the readings by using the following formulas, in which T and F are the temperature and the frequency respectively. And it says voltage range 150, 300, 600. And the resistance is shown as 3822 at 25 degrees Celsius, or 7644 for the 300 volt range, or 15288 for the 600 volt range. To correct for temperature readings, multiply by, and it's compensated for 300. You have to multiply by, what is that? 1-0.000 comma 10 T 25 degrees, etc. So there's a bit of a formula there. Instruments having ranges of 7.5 volts or less should be used with 0.026 ohm leads. Approximate self-inductance of field and movable coils at full scale blank Henry and half scale blank Henry. October 17th, 1952. So even though this meter type dates earlier, this particular example apparently was adjusted in the factory in 1952. J.B. Dowden. You don't see much of that kind of thing anymore. Here's what the case looked like when I first got it. You can see a lot of debris up near the vent on the left side, and also the case front panel support bracket at the lower right corner is gone. Also, you can see the original handle in its cruddy condition at right. Here's a view of a support bracket that isn't broken. Here's where I've put some epoxy on the corner and also filled the stripped out holes for the one bracket. I used a little plastic hand-operated pin drill to get into that tight confine and put pilot holes into the epoxy, and there's a piece of blue masking tape so I don't accidentally drill through to the other side. Here's after the pilot holes have been drilled in the epoxy. And the bracket is ready to be screwed into position in the repaired holes. I used my micro right angle ratchet screwdriver by Chapman to drive in these screws. I couldn't fit any other screwdriver in there. Either they were too long or too wide or something was wrong. But this worked great. I also epoxy stabilized another corner. I forget which one now. I think it's the lower left-hand corner in this picture. And I also did some cleanup around the inside of the case and the inside surfaces of the perforated metal ventilation plates. Here are more views of the original handle. You can see why it's not horrible off on the right side. The left side was almost coming apart. It was just crumbling. And to give the handle some shape, you can see there's kind of a rolled paper thing that's sewn inside the leather. It's kind of a white color there. I'd supplied the handle with the original metal brackets screwed to a piece of plywood in order to show the leather worker, my shoesmith, what the spacing was so he could contour the handle properly. And this is the way I got it back from him.